Let's look at some more examples in section 6.6, solving equations with logarithms and exponentials. This one here, we have 10 over 1 plus e to the negative x equals 2. Now, at the moment, this is not any of our types. So let's do a little bit of manipulating first. Let's start by multiplying both sides by 1 plus e to the negative x. That's going to allow us to cancel out that denominator and make our equation just a little bit more simple to start out with. So then we have 10 equals 2 times 1 plus e to the negative x. This is starting to look a little bit like variables in the exponent. So I think what I want to do is try and isolate that base up to the power. So my next move, I could distribute the 2, but I think what I'll do instead is divide both sides by 2. So then I have 5 equals 1 plus e to the negative x. Then subtract that 1 over, so we have 4 equals e to the negative x. And now I can see that it is variables in the exponents. Okay. So my strategy when I have variables in the exponents is to isolate the base to the power, then take the log of both sides. So I will go ahead and take the natural log of 4 equals the natural log of e to the negative x. And then that's going to allow me to bring this exponent down in front. So I have natural log of 4 equals negative x times the natural log of e. Now I remember that that natural log of e, that's one of my properties that we learned. I don't even remember what section that was, 6.5 I think, that the natural log of e equals 1. Also think about this log is asking us the question, the base, which is e, to what power gives me e. So we know the natural log of e is 1, so that we can then just make this natural log of 4 equals negative x, which would give me x equals negative natural log of 4. So that's one answer. That's one way that we could give that answer. We could say x equals negative natural log of 4. But we could get fancy if we wanted and make that a negative 1 times. And then we could bring that exponent up top. So we get natural log of 4 to the negative 1. And that negative 1 exponent means to move the base to the denominator. So another way to write this would be x equals the natural log of 1/4. So either of these, I would say, would be acceptable answers. Now let's talk domain. Remember, we have 3 things that we need to look at. One is if we have an even index radical with variables, which we don't. One is logarithms, which we don't have. But the other is variables in the denominator, and that we do have. So our strategy when we have variables in the denominator is to just take that denominator and straight off set it equal to 0, because that's what we want to avoid. So we want 1 plus e to the negative x to not equal 0. So in other words, e to the negative x should not equal negative 1 if I move that over. And e to the negative x means 1 over e to the x, so that should not equal negative 1. If I multiply both sides by e to the x times e to the x times e to the x, then that gives me 1 cannot equal negative 1 times e to the x. Then if I divide both sides by -1, that gives me -1 should not equal e to the x. That was a lot of manipulating to get to the idea of thinking about the graph of y equals e to the x, having its three special points at -1, 1 over e, which is about 1/3, a little smaller than a third, and then 0, 1, and then 1e, which is about 2.7. So y equals e to the x looks like this. And y equals -1 is down here. So you can see that y equals e to the x and y equals -1 never cross. So e to the x never does equal -1. So that means we have no domain restrictions. And the domain would be -infinity to infinity. So that whichever version of our answer we choose to use would work. Remember that these are the same. Okay, this problem right here. This is all logs with the same base. The strategy that we talked about when you have all logs with the same base is that we should combine our logarithms so there's only one log on each side of the equal sign, and then use the one-to-one property, and finally to solve for our variable. So I will combine these two logs on the left side to make it log base 4 of, remember when two logs are added, they combine by multiplication. So that will be 3x plus 12. And on the right side, log base 4 of 5 plus log base 4 of 2x minus 3 becomes log base 4 of 10x minus 15. And now I can use the one-to-one property. And that allows me to set 3x plus 12 equal to 10x minus 15. And go through the solving steps. So I'm going to go ahead and subtract my 3x over and add my 15. So that gives me 27 equals 7x. Divide both sides by 7, and there's my answer, 27 over 7. Let's check against our domain because we did have logarithms in our problem. We need to check to make sure that the argument is greater than 0. So x plus 4, we got to figure out what makes that greater than 0. 3 already is greater than 0. 5 already is greater than 0. And we need to check 2x minus 3 to make sure that stays greater than 0. So for our domain checks, we're going to be looking at x plus 4 greater than 0 and 2x minus 3 greater than 0. So x is going to need to stay greater than -4 for this one, and x is going to need to stay bigger than 3/2 for this one. Since this is the more restrictive, our domain is going to be limited to 3/2 to infinity. 3/2 is like 1.5. 27 over 7 is bigger than 4, so this value is fine. E to the negative c equals 6 to the 7c. This guy is variables in the exponents. We can't make these have the same base. I can't change an e into a 6. I can't change a 6 into an e. So I'm going to have to take the natural log of both sides because that's the strategy when we have variables in the exponents. So here we go. Natural log of e to the negative c equals natural log of 6 to the 7c. Now the reason that we use that strategy is so we can bring those exponents out front, which gets the variables out of the power. And that makes it easier to solve. So we have negative c times the natural log of e equals 7c times the natural log of 6. We've already seen earlier that natural log of e is 1. So this is essentially negative c equals 7c natural log of 6. This type of situation is going to happen multiple times where we have two of our variable, like two terms that have the variable we're trying to solve for. So let's go ahead and write ourselves a little note, like talking about how to deal with that, like what strategy to use. So we'll put that over here. I think we've seen them before, but it's probably worth writing out again. So when more than one term has our variable, and it's linear, like they're not, none of them are squared, so it's not a quadratic equation. So what we are going to do is we are going to move all of those terms that have our variable to the same side of the equation. Then you're going to factor out the variable. In this case, it's going to be a c, so we'll have c times some parentheses. And then divide both sides by the parenthesis. So that's going to be our strategy. More than one of our terms has the letter c, so we're going to move all of those terms to the same side. So I'm going to go ahead and add the c over to this side, which is going to give me 0 equals c plus 7c natural log of 6. Then I'm going to factor out a c, so I get 0 equals c times 1 plus 7 natural log of 6. Then I'm going to divide both sides by that parenthesis. So divide both sides by 1 plus 7 natural log of 6. And in this case, it actually just ends up giving me c equals 0. Now, looking back at our original problem, do we have any domain concerns? I'm going to squish that in over here. Domain. We did not have any variables inside even index radicals. We did not have variables inside logarithms. And although e to the negative c equals 1 over e to the c, e to the c never equals 0 because it's that exponent function that we just looked at a couple problems ago. So that's not going to give us any restrictions. So our domain is not restricted. So it'll be negative, and why two negatives? Negative infinity to infinity. So c equals 0 is fine. Okay. Let's see what's up next. This one looks complicated. So I'm going to tell you a strategy to start out with that's going to help us uncomplicate this problem a little bit so it'll be easier to deal with. We are going to start by multiplying both sides by that denominator, just so we have a little less, awkwardness to deal with. So those denominators are going to be out of there. And then we'll have e to the x plus e to the negative x equals, I'm going to distribute that 3, so 3 e to the x minus 3e to the negative x. Okay. Now I want to think about what that negative exponent means. So since e to the negative x means 1 over e to the x, I'm going to rewrite those terms in that manner. So I'm going to have e to the x plus 1 over e to the x equals 3e to the x minus 3 over e to the x. There's more than one way you can deal with a problem like this. We could have combined like terms up here. We could still combine like terms on this step. There will be another opportunity for us to combine like terms in a moment. What I'm going to do at this point is clear the fractions. So I'm not dealing with over e to the x anymore. So I'm going to multiply each term by e to the x. Because then what that's going to do is cancel out these denominators. So I'll have e to the x times e to the x. Remember, when you multiply the same bases to exponents, you end up adding the exponents. So we'll have e to the 2x plus 1 equals, this becomes 3e to the 2x minus 3. And now it's a little bit less intimidating, I think, to combine like terms. So I'm going to add my 4 over to that side and subtract e to the 2x to this side. Oh, that's not a 4. Hi, that's a 3. I mean, 1 plus 3 is going to give me 4. So there's that. So I have 4 equals 3 minus 1, so 2e to the 2x. And we're almost at that variables in exponents. But we're also almost to where we can go ahead and convert. But first I'm going to need to divide both sides by 2 so that I have my base isolated. So 2 equals e to the 2x. Now from here I can either take the natural log of both sides, or I can convert to exponential form. Either way is going to give me the same answer at the end of the day. So whether you want to take the natural log of both sides or just convert to exponential form, that's going to be, convert to logarithmic form. That's going to be your choice, but we'll get the same place. So I'm going to choose to convert to logarithmic form. So that means my e that's in the base is going to become the logarithm base e, which is a natural log. So I'm going to have the natural log. It's going to leave the exponential relationship with the 2x and become in a logarithmic relationship with the 2. So natural log of 2, and then the 2x is going to be the single, so equals 2x. And then to solve for x, we just simply divide both sides by 2. So we get x equals the natural log of 2 over 2. Now, our original problem had all e to the x's and e to the negative x's, and we know e to the x can never equal 0, so having that in the denominator is not a problem. Then we look here. I just want to double check and make sure that you guys are all on the same page, knowing that we can't simplify the 2 that's in the log with a 2 that's not in a log. So think about it like square roots. If I had the square root of 2 divided by 2, I could not simplify the 2 that's inside the radical with the 2 that's not inside the radical. It's kind of the same thing here. A natural log, or any log, is a mathematical operation that would be on the same order of operations level with exponents. So since exponents would come before division, logs also go before division. So I would have to do the natural log first before I could do the division. So that is as simple as this can get. Okay, 3 to the x plus 2 equals 5 to the x minus 4. Now this one is variables in exponents. They do not have the same base. There is no change of base formula for exponents. That's only for logarithms. So our strategy for variables and exponents is to isolate the base to the power, which they are isolated, base to a power, base to a power. Then we are going to take the log of both sides. I will choose to use natural log so that we can bring the power out front, and then we're going to solve. So we will start by taking the natural log of both sides. I'm going to have natural log of 3 to the x plus 2 equals natural log of 5 to the x minus 4. And the reason we do that is so we can bring these powers out in front. When you bring the powers out in front, you have to make sure that the x plus 2 sticks together. I can't just write the x plus 2 without the parentheses because then I will never remember that they were together in that exponent. So x plus 2 parentheses times natural log of 3 equals x minus 4 in parentheses times natural log of 5. From here, we are going to want to distribute our natural logs of 3. So we're going to distribute the natural log of 3 to both of these terms, and we're going to distribute the natural log of 5 to both of these terms. So where does that leave us? We have x times natural log of 3 plus 2 times natural log of 3 equals x times natural log of 5 minus 4 times natural log of 5. Okay, where can we go from here? I mean, I suppose we could bring these powers up front, up top. That's going to be a big number, 5 to the 4th. I would say that's not like an absolutely necessary step, but it's something we can do. Gosh, what is that? 5 to the 4th. 625. Oh, it's not too bad. Okay. So a couple of things to keep in mind. All of our logs are just numbers. Like natural log of 3 is just a number. Natural log of 9 is just a number. Natural log of 5 is a number. Natural log of 625 is a number. So in dealing with all of these, like they're just numbers. So this would be like a 7x plus 2 equals 12x minus 87. Like we're going to be manipulating things in similar ways that we have before. So we're going to want to move all of our terms that have the variable to the same side and all of our terms that don't have variables to the opposite side. So I will subtract my natural log of 9 over to this side. And I'm also going to subtract x natural log of 5 over to this side over here. So then I have x natural log of 3 minus x natural log of 5 equals, these are not like terms because although they have the same base, they do not have the same argument. So they cannot be combined with each other. So negative natural log of 625 minus natural log of 9 is as good as it gets. But now I have that situation where I have two of the same variable, like we did on our previous page. So we're going to use that same strategy that we used before. When more than one term has our variable, move all of those terms to the same side, factor out the variable, and then divide both sides by the parenthesis. I have lost my red pen, so I cannot exactly write that again. Oh, found it. So we are going to factor out the x. That's my first step. And then divide both sides by the parenthesis. Divide by both sides by natural log of 3 minus natural log of 5. And I'm going to end up with x by itself equals negative natural log of 625 minus natural log of 9 divided by natural log of 3 minus natural log of 5. And that's really all we're going to do. We're not going to do any more simplifying, although there are other things you could do to change how that looks. I'm totally fine with it staying that way. I would have been totally fine with you leaving 2 natural log of 3 and 4 natural log of 5. So that's fine as well. Let's think about domain. In our original problem, we did not have any logarithms with variables. We did not have any radicals with variables. We did not have any denominators with variables. So there are no restrictions on our domain, making our domain negative infinity to infinity. So this answer is perfectly good. Unless they want a decimal approximation, and then you'll need to use your calculator. All right, speaking of calculators, this is our last problem in this section, and it is wanting us to find an approximate solution using your graphing calculator. So when we had previously in other sections looked at solving equations by graphing, our approach was that we would put y1 in the left side. In y1, we would put the left side of our equation. In y2, we would put the right side of our equation. So that's what we're going to do. So y1, we are going to put in the left side of the equation. In y2, we're going to put the right side of the equation. Now, if you have the log base feature in your calculator, this is going to be a lot easier for you to graph. If you don't have the log base feature in your calculator, you're going to have to use that change of base formula. So I have it. Clear. Oh, I have a lot of things in here. So in y1, I'm going to put math log base 5 of x plus 1 minus log base 4 of x minus 2. And in y2, I'm going to put 1, except for I typed 2. And then we're going to look at our calculator. So I'm going to do zoom standard. Now, remember that these calculators are not very fond of graphing functions that have vertical tangent lines or get really big really fast in a vertical direction. So it does not like this logarithm graph. But we know, based on what we've studied so far, that this graph actually does continue going in the up direction. So when I go to graph this on my paper, I know it's kind of continuing on like that. So this is my y1. It was blue in my graph. And my y2 was red, and it's just a horizontal line. Y equals 1. So there's my y2. And then for my solution, what I'm looking for is this ordered pair right here. So after we put y1 in the left side of the equation, y2 in the right side of the equation, we want to look at the graph. And what I did was zoom standard, but you'll need to be able to locate the intersection or intersections visually. So you have to be able to see them on your graph or the calculator can't find them. And then we're going to do second trace. Second trace is going to be the calculate menu. So second trace gives me the calculate menu. And I am looking for the intersection. So I want number 5. So number 5, which is intersect. And then I'm just going to hit enter 3 times. So enter, enter, enter. Oh, it didn't take. Oh, it didn't take because I'm not on my first curve. So that's an issue. So I'm going to scroll to the right until I end up with a y value for my first curve. So I'm just going to keep hitting the right arrow. And there it is. So then I hit enter, and then enter, and then enter. And it tells me my intersection is x equals 2.7871804 and y equals 1. So let's write those instructions down. Enter, enter, enter. Just remember that if your little spider is not showing up, you need to arrow until you end up on the spider. Enter, enter, enter. Then it's going to give us the intersection ordered pair. So here we had 2.7871804, 1. And what we were trying to solve for was the x value. And the y value is where they, that's how I know that they are intersecting, is because their y values are equal. So the y value is irrelevant in solving this equation. The answer would be the x value. So 2.7871804 is the solution. So let's write that down over here. X equals is the solution.